All right. So, sorry, I need to share my screen. No, like this. And one screen is this one. Okay. All right. So let's see, where was it? Yeah. So today's lecture is gonna be about two loops and generalization to higher loops. So the one loop case, it's somewhat peculiar. I mean, it's very simple, so it lacks some of the features of the other ones. So first of all, we have to understand what kind of diagrams can we have. What kind of divergent diagrams can we have? So the simplest case at higher loops is to simply insert a divergent one loop diagram. So the one loop diagram to be a subdiagram, or generally in the n loop to have a divergent n-1 loop subdiagram. So that's the case I've written here. So as you can see, why do I? Sorry. Sorry. It's very hard to use this thing. All right. So this is obviously a one loop subdiagram, and it's divergent. We've calculated it, right? And moreover, we know how to calculate it. So we can also, as I said before, the counter terms can be inserted into higher order diagrams. So in particular, this one loop diagram was cancelled by a counter term of this type. So we can also insert this into a two loop, quote-unquote two loop diagram. Remember, I also said that what we're really counting when we say loop order, we're counting the powers of the coupling constant, right? So this might look like a one loop diagram, but since it has the counter term inside it, and the counter term has an extra two powers of the coupling constant, so it's appropriate for a two loop diagram. So, and we also know that therefore that the divergent parts of this and this will cancel. So also the divergent part of this and this will cancel as far as this type of divergence is concerned. However, the other possibility is that there are intrinsically divergent two loop diagrams, or in general n loop diagrams. So this will be cancelled, well, by adding, in principle, new n loop counter terms. In this case, two loop counter terms. That is, we correct again the Lagrangian, the parameters of the Lagrangian, by objects at this the corresponding loop order. So let's look here. Well, no. First of all, let me remind you. Let me tell you that in fact there's a further subdivision of these intrinsic two-loop divergences. There's one that are independent diagrams. For instance, well, wait a minute. Well, anyway, I seem to have the wrong kind of example in here. Anyway, in principle, there could be intrinsically two loops. So in this particular case, I could have, for instance, one more photon line. So that would be intrinsically two loop and also independent, right? But the other possibility, so these are divergences that are polynomials in the momentum squared. Although in principle you could have a logarithmic divergence, so log lambda squared. But polynomial is in Q squared. Why? Because polynomial is in Q squared means that Fourier transform of that in X space is also a power. So that means that this is local. Local means there's a single power, so something like 1 over x to the power alpha. But if you have something like a log is really an infinite series of powers, thinking about it in Taylor expansion. So an infinite power series is by definition non-local. I told you that, for instance, a non-local example is the exponent of p squared, right? The exponent of p squared in X space would be exponent of del squared, and the exponent of del squared acting on a function means really the Taylor expansion of f of that function depending on x plus an extra thing. That's non-local. It depends on x and x plus that thing, right? So to summarize, powers in Q squared means local terms. Log in Q squared means non-local terms. So the other possibilities is to have nested or overlapping divergences. In this case, you have the two divergent loops inside the two-loop diagram share a propagator. And these will correspond to non-local divergences, that is non-polynomial, like logs in Q squared. The example, one example I wrote here, so in the 5-4 theory that we're gonna be calculating, is either this, the setting sun, or this, which is a little bit, so this setting sun is for a 2-point function, and this is for a 4-point function, where I basically just added one more vertex to have 2 more external lines. So in this case, you see this loop and this loop share a propagator, unlike this case. So this divergent does not share any divergent. So if I would have, let's say, this and another loop here, they would not share any propagator, so there would be independent subdiagrams. There would be subdiagrams that are independent. So in this case, okay, so let me also give the relevant example for QED, which is the physical case. So one example is written here. So this would be a 2-loop correction to the fermion propagator. So we've calculated the 1-loop correction to the fermion propagator. That was just, you know, this photon line making a loop on the fermion line. Now I'm saying it's so the nested case is this one. I have this loop and this loop sharing this propagator. Okay. The other possibility is for a correction to the photon line, photon propagator. So this is the photon propagator. Now what we've calculated was just this one loop fermion inside the photon propagator. But now I divide that photon, fermion loop, that electron loop, by another photon propagator. And now this loop and this loop share this photon propagator. Now, to understand this, to understand what's happening here, imagine moving this photon. I mean, this is a diagram, so it doesn't really matter where I put, because you integrate over things. But imagine that I draw it a little bit to the left, a little bit to the left, something like this. If I draw it like this is the same diagram, just drawn a little bit different. But now if I draw it like this, you note what happens. You note that there is actually so inside this 2-loop diagram, there's a correction. There's a 1-loop correction to the vertex. This diagram. So as you see, this one is just this, right? It's just the 1-loop vertex correction inserted inside the 1-loop correction, 1-loop fermion correction to the photon propagator, right? So the divergence shares a propagator. Well, shares this whole propagator. So what happened? Well, let's try to understand now the mathematics of it. So why is this a non-local term? And what's this? What's the divergence? Well, we have seen that the one loop divergence to the photon fermion vertex is of this term. So there's the classical part, minus IE gamma mu, and then it's multiplied by this divergence part, which was alpha log lambda squared, right? On the other hand, we insert this correction. This correction was inserted inside the one loop, the fermion one loop correction to the photon propagator. And that, in turn, we've seen that is of the type g mu nu q squared minus q mu q nu, pi of q squared, right? And then so this pi of q squared has, since it's one loop, its alpha dependence is just a common alpha. So that means that really the structure of this whole divergence is first that divergence coming from this this vertex, and then the divergence coming from the one loop. So the product of the two. So it's alpha g mu nu q squared minus q mu q nu times log. And we also seen that pi of q squared goes like log lambda squared plus log q squared. So then we have alpha g mu nu q mu squared minus q mu q nu times this pi, so log lambda squared plus log q squared, times alpha log lambda squared. So that was the correction for the vertex. So that means that inside this, there's a part that depends like log q squared times log alpha squared, and then there's also two alphas. So this part is divergent in lambda, right? When lambda goes to infinity, this log lambda squared goes to infinity. However, it's non-polynomial in q squared. As I said, log q squared is non-polynomial, which means it's non-local in X space. So the reason why this is non-polynomial is because it comes from the divergent part of one divergence, right, times the finite part of the other divergence. All right. So as I said, then in X space, you make a Fourier transform to X space, then this is not local anymore. So this has to be cancelled by something else. It cannot be cancelled by a purely two-loop counterterm, because it's not local, and the Lagrangian is local. So the only possibility is to be cancelled by something that is divergent, so something like a one-loop diagram. But in it, you have a counterterm, but the counterterm is one loop. So it's the one-loop counterterm inserted inside the one-loop Feynman diagram. All right. So, as I emphasized also in a previous lecture, the counterterms cannot be can be put into anywhere into a Feynman diagram. So once you've defined a counterterm, that's part of your Lagrangian. So that has to appear in the Feynman diagrams. All right. So the possibilities to cancel this divergence is to put this counter term to the vertex inside the one loop diagram. So you can either put here and then the other one, the other vertex is uncorrected, or you correct this one and this other one is uncorrected. Of course, when you look in here, there's also log lambda squared times log lambda squared. So there's this term alpha squared times log lambda squared. However, in terms of x dependence, this is local, right? This is, in fact, x independent, is a constant. So this must be cancelled by the addition of a new two-loop contribution to the local counterterm Lagrangian. So this is a two-loop counterterm vertex, right? So we defined before this one-loop counterterm vertex. Now we have to add also a two-loop contribution to the counterterm vertex, the two-loop vertex. So this procedure that I described for you today generalizes in an obvious manner to all loops. It just becomes more cumbersome, more complicated, but it's the same idea. And it is a non-trivial fact that in this way we can cancel all the divergences of the theory with a finite number of local counterterms, such that we can renormalize the parameters of the Lagrangian. Right. So that means that the counterterms, you know, A, B, C, and Z, the way we defined it before for 5 to the 4, there, as I wrote there, there's a infinite infinite expansion in powers of the coupling that is in loops. So this is true if the theory is renormalizable, which we know how to define. So the theorem proving this fact, that any superficially divergent theory is in fact rendered finite by these counterterms, by canceling Feynman diagrams in this way, is known as BPHZ theory, after Bogolubov, Parashuk, Hepp, and Zimmermann. By the way, it's not our Zimmermann. Our Zimmermann has one N. All right, so this is all the theory, but now we will calculate the actual mathematics of the two-loop, the cancelling of the two-loop divergences in the simplest example of renormalizable theory that we have, the 5 to the 4 in 4 dimensions. All right, so what kind of two-loop diagrams do we have? Well, we can organize them in the following way. So we have 5 basic diagrams, which we call in the S channel. And then we use crossing, the idea of crossing, of going to what we called the T channel and U channel by flipping. Remember how crossing was defined, by flipping the external lines in terms of in and out. So these basic diagrams are 3 diagrams without counterterms and 2 diagrams with counterterms. Right. So the most obvious one is when you put this kind of chain of one loops. You put one loop and then another one loop. The other one is this nested one, that I define. But this one is asymmetric, so you can also do its mirror image. You can also add this mirror image. And then, as we said, we have to add the one loop diagram with one of the vertices being the one loop counterterm vertex. So this one or this one. All right, and then the other ones are obtained by crossing, by applying crossing into the T channel or into the U channel, meaning flipping the in and outs in this way. Oh, and finally, of course, as we said, we also have to add an intrinsically two-loop vertex correction. So this is the 4-point function, so therefore you can think of this as a correction to the 4-point, the vertex of the 5-4 theorem, which is this. All right. So therefore, in order to fully renormalize 5-4 at two loops, that means we only need to consider these S-channel diagrams, because the other ones are trivially obtained by crossing, plus this intrinsically two-loop counterterm. So what we have to consider are these diagrams. All right. So since, as we said, we have to also consider the one loop insertion of one loop vertex correction, let's remember how that was. So one loop renormalization was something like this. There was one propagator with a Q and one with a Q plus P, then integrated with a symmetry factor 1/2 because of flipping, and with lambda tilde squared. This depends on a P, and I've written this in the S channel. That means P, the summing of two incoming momenta, is P1 plus P2. Then when I cross, it will be something else. If it's P1 plus P3, then it's U. If it's P2 plus P3, then it's T. All right, and then this integral we've calculated and is given here. The next thing to do is to consider a normalization condition. Okay, so we could have used a minimal subtraction scheme, but it's not useful. What's more useful is to consider normalization condition, and also more physical. As I said, this corresponds to something physical, that the propagator at some scale is given by the classical one, and the vertex is also the classical one. So the normalization condition is given at S, so incoming energy squared for equal to 4m squared, and T equal to U equal to 0. And I define S as P1 plus P2 squared with a minus in front. Well, the minus with plus or minus, that's conventions. So then the one loop counterterm vertex is this integral I2, which depends on this P. on p squared. But so lambda squared over 2. But then this I2 depending on S, which is minus P1 plus P2 squared. Right? And S is equal to 4m squared for our normalization condition, plus then I of T, in which case P is P1 plus P2 plus P3. But in our normalization condition, T equal to 0, plus I of U, in which case P is equal to P1 plus P3. So, and the minus is, is because, well, now, why is it the minus? Yeah, I'm not entirely sure why there's a minus, but that's probably just typo. Oh no, sorry. Yeah, I'm talking about. Yeah, I'm an idiot. Yeah, I'm talking about the counter term. So this is the Feynman diagram, and the counter term is with a minus, right? All right. So this is our one loop counter term vertex. Now we split this into the S part. The S part, as I said, is this one. And then a T plus U piece, which is this one. There was one T equal to 0 and one U equal to 0. All right. And then we've split, as we said, the S channel diagrams. The diagrams as S channel, U channel, and T channel. All right, so let's write this more precisely. So we had these three diagrams, which were the S channel diagrams without counter terms. And now we had two diagrams with counter terms, but we split the counter terms into S and T plus U. So there was this diagram, and we split it into S and T plus U. And there was this diagram, and split it into S and T plus U. All right. And then we split, we arrange them into the way that I've written here. Type 1 diagram, type 2 diagram, type 3 diagram. And the reason is that, in fact, in each grouping, 1, 2, and 3, the divergences will cancel. The momentum dependent divergences will cancel. All right, so let's see how that works. So the first one, the first divergence is this chain of, there's a one loop, and then I glue it to another one loop. So the result of the diagram is then simply this one. It's I2 of p squared, which is the one loop integral. So this is a one loop integral, right? But then this is also a one loop integral. The only thing that's bizarre is that if I write one loop, if I write one loop, the one loop diagram, I write it for the 4-point function, so I write it like this. Or if I write it for this, then I write it like this for this 4-point function. But now I write it, I put them together for the 4-point function. And the integral is still an integral, right? And what's different? Well, the sum, this depended on the sum of these two momenta, but the sum of that is equal to the sum of this by momentum conservation, so that doesn't matter. So really, the result for this is just the product of the two one loop integrals, so I2 of p squared squared. And the only difference is that the dependence on the dependence on lambda tilde. So there's 1, 2, 3, right? So there's lambda tilde squared cubed. And the 1 over 4, it's also because this is I2 over 2, 2 being the one loop symmetry factor, which is still preserved. Yeah, and the minus is because actually the vertex is minus lambda tilde. So it's minus lambda tilde to the cubed, as opposed to before where it was minus lambda tilde squared. So, all right. So how does this cancel with the insertion of VS1 up and down? Well, let's see what that other diagram is. So what's this diagram? Well, the integral is again the same integral as here and here, is the one loop integral, I2 of p squared. Right? So there's this again is p squared, so this integral is I2 of p squared. Okay, I2 of p squared. And then times the vertex minus lambda tilde, and exchanging these two lines, there's again the symmetry factor 1 over 2, so minus lambda tilde over 2 I2 of p squared. Okay, that's the part that depends, that's independently one loop. But then I have to put the one loop vertex counter term. Right, so I have to put this, moreover, only the S part. But I know what that is. I've calculated it. That was this, minus lambda tilde squared over 2 I2 of 4m squared. So I multiply with this, and together I get this result. And so I sum this with this first term. And then I have to also I have to also sum the one with S downwards. Yeah, so I've rewritten them. Sorry, I've rewritten them like this. So minus 2. So there's these two Feynman diagrams are equal, right? It doesn't matter if I put the vertex here or here. the counter vertex here or here. It's the same result. So I have a -2 times this, and then I rewrite this as I2 of p squared minus I2 of 4m squared, everything squared, plus a constant, minus a constant, so this one. However, this thing inside the square, so this thing, is actually finite, because this is the same thing that appears in the renormalization at one loop. This was the thing appearing from the Feynman diagram, and this was the renormalization factor, the counter term, right? So the result of this was equal to this. Okay. So there's the canceling of the divergent 1 over epsilon terms, which are p independent here and here m independent. So the 1 over epsilon term cancels, and then this, what remains is finite. And moreover, we also canceled this psi of 1, which is minus the Euler constant. And so the result of this term is, this first term is this. All right. So what does that mean? That that means that, so let's remember our general theory. So in this grouping, we have canceled this, which was an independent one loop subdiagram, and we have canceled it with the one loop counter term. Well, yeah, with part of the one loop counter term here and here. But we're also left with this term, which, however, it's constant, meaning it's not dependent, it doesn't depend on p squared, but it's still divergent in the sense that it's 1 over epsilon. However, this is squared, so it's actually 1 over epsilon squared. So what we're left with is a correction to the two loop, the intrinsic two loop counter term. So this thing will be a vertex of the type 1 over epsilon squared multiplied by lambda tilde cubed. So lambda tilde cubed means two loop, and this correction is of the type 1 over epsilon squared. Right, so it's a higher order pole in epsilon, whereas at one loop we only found 1 over epsilon terms. So one observation is that, as I say here, in all cases, the highest order in epsilon, in this case it's 1 over epsilon squared at two loops, will be momentum independent, like this one. This one only depends on m but not on p. The other observation is the functional form of the finite part. So in this term, the finite part, in this finite part, so this is divergent, but in this finite part, this one depends on log of, so if I divide by m squared both the denominator and the numerator, we see that depends on p over m squared. So actually this whole thing will depend on log p squared over m squared, at least if p goes to infinity, because in that case I can just ignore the 1 in here, and then I just have log of, so this cancelled with this is ignored, and then I get log of p squared over m squared, 4m squared. So when p squared goes to infinity, this one depends on log of p squared over m squared. So this functional form was the one loop functional form. But now at 2 loops, I have this thing squared, right? So at 2 loops, I have this kind of correction. And this came from the 2 loop chain of 2 rings. But then we see that we can easily generalize these to n loops. So on n loops, I can write n rings like this. I mean, I wrote it badly. I wanted this to be curved in the sense that it just continues. There are n loops in here. So let's say like this, and like and like this. Anyway, and like this, and like this. And so these are all n loops, and these will all so at n loops I'll have lambda to the n plus 1, and then log p squared over m squared to the n, right? All right, so until now I've considered this first set of Feynman diagrams. Now let's consider this second set of Feynman diagrams. All right, so the one without counter terms, without counter term vertex, is written here with momentum identified. So at p1, p2, p3, p4. And I call this k plus p, and then in here I have k plus p3, which also must be equal to by convention no, sorry, yeah, this thing is yeah, then this thing is whatever it is the difference between this all the, or rather the k plus p3 plus p4 minus wait a minute, I think I may have done No, it's like this. So let's see. So this line would be k plus p3 plus p4 minus no, k plus p minus k plus p3 minus k minus p3 minus p4. Minus p3 minus p4 is equal to minus p1 minus p2, which is p. So it seems to be 0. What happened here? No, it's yeah. It's just wrong. Yeah, it's just wrong. Yeah, it's a two loop. Yeah, this would be a Q. Then this would be, so P3 plus P4 minus P cancels. So this would be Q minus K. Right. By the way, you can correct me if I say something stupid. So so my point was that I can isolate this one loop diagram. This is a one loop sub diagram of the two loop diagram, and so no, wait a minute, this. I kept writing k plus p3, but that's not right. All right, so the integral, it has indeed this propagator, which is 1 over k squared plus m squared. Then this other propagator, which is 1 over k plus p squared plus m squared. It's integral over k. Yeah, of course. But yeah, I wrote this completely wrong. But this depends on the external momenta. So the external momenta at this vertex are k plus p3. I can also say as k plus p plus p4. Well, sorry. I could say minus k plus minus p plus p4, but then this would be minus k minus p3 by momentum conservation. So it's still the same thing. So this is k plus p3. So this one loop subdiagram depends on the external momentum going out at one of the vertices, either here or here. Like here it is one going in, one going out, and there's more stuff going. So I can write it simply here. So this depends on k plus p3, right? So it's the one loop integral I2 of p squared, but p in here is k plus p3, the external momentum at one of the vertices of the one loop subdiagram. So this is the I2 of k plus p3. But this I2, and of course, this depends on minus, so the vertex is minus lambda tilde to the cubed. That means that's minus lambda tilde cubed. And there's a symmetry factor of 2 because I can just flip this side with this side. And so I get 1 over 2. So that's the result of the Feynman diagram. Now, the product of these two propagators can be replaced with the usual Feynman parameterization integral over a parameter that I'll call beta. So I write this integral over beta, and now this depends on k squared plus 2b beta k dot p plus beta p squared plus m squared squared. All right. But then this integral I2 also is written in terms of an integral of an alpha, and I know it. It's integral over alpha of this. It's over this because here I already shifted. I already shifted k so that I already shifted this momentum so that I don't have the part linear momentum. But now the result of this integral, is dimension dependent. So this depends. This is at the power 2 minus d over 2, and d is not an integer now. So now there's a problem. Now I cannot use again a Feynman parameterization like I would do it before if I would have the product of, you know, 1 over some propagator squared plus 1 times 1 over some other propagator squared. Then I simply write one more Feynman parameterization. But since this is a non-integer power, I cannot do this. So I have to do something else. And the something else that I do is this formula. So now I have to use formula with arbitrary powers. So 1 over a to the alpha, 1 over b to the beta, where alpha, beta now are arbitrary real parameters. I mean, I suppose it could be also complex, but real, it's fine. So the formula that I wrote is here. This is again an integral over some Feynman parameterization like parameter. So an integral over something dw going from 0 to 1. And I also have this something that depends on both a and b to the power alpha plus beta, but now it's a little bit more complicated. right? So now I have w to the power alpha minus 1 and 1 minus w to the power beta minus 1. And in here, I still have the same thing as we had before. In the usual Feynman parameterization, I still have WA plus 1 minus WB. Now, this constant that depends on alpha and beta is actually the inverse of the beta function. So Euler gamma function is gamma of alpha, but gamma of alpha, gamma of beta divided by gamma of alpha plus beta is known as the beta function, Euler beta function, B of alpha beta. All right, so to prove this, well, we define this complicated variable, z, that depends on a and b in this way. 1 minus z is this, then dz, you can calculate it to be this. And so this integral over w is written as an integral over z, but now it's really 1 over a to the alpha, 1 over b to the beta, which goes outside. And then this integral is independent of a and b. Is just a constant, and moreover, this is the definition, an equivalent definition of the beta function. So this gives beta function divided by a alpha and b beta. So to finally prove the formula, you just divide this by the beta function. So we apply this formula to our case. I have A is this thing, alpha is 2, B is this thing, and beta now is non-integer, 2 minus d over 2. Well, or I guess I put the other way around. I switched alpha and beta, and then b, whatever. The result is the same. So the Feynman diagram now is again an integral over 3 Feynman parameterization like parameters, alpha, beta, and w. And I still have the integral over k to take care of. So this part is easy. I have just this quadratic part, so k plus p3 squared. But here I have k squared and a linear term, so I have to get again. I have to again shift k by p. By a p-dependent term to cancel this term linear in k inside this whole bracket. So I define now the shifted k prime is k plus this thing that depends on p. It also depends on p3 because there was already a shift in here. So defining this complicated shift, I find again the same kind of thing that we obtain in the Feynman parameterization, namely k prime squared divided by multiplied by something that depends on these integrated parameters, and then some constants. I mean, k independent constants. I have this p that is a combination of p and p3 and so on. Is this thing. and then I have also m squared. I mean, I could as well write this as part of p squared, but whatever. The point is, I guess, that when p and p3 is 0, then this whole thing is 0. Yeah, and for future reference, we'll also note that when w goes to 0, we'll see why w going to 0 is relevant to our analysis of divergences. Then p squared becomes, so let's see here, when w goes to 0, this term goes away, this goes away, so it's p squared beta that remains. And here, this term goes away, this away, this away, this away. So the only thing that remains is this beta p, everything squared. Right? So it's p squared beta minus beta squared p squared. So beta 1 minus beta p squared. All right. So now we can finally do the integral of a k, which is the same as integral of a shifted k, k prime. We did several times, so we can do the integral over this loop parameter and find a result that now depends only on the Feynman parameterization parameters alpha, beta, and w, and the external momentum. Right. So so this is the form. Yeah, I just simplified. I mean, I just wrote this on top of this thing, and the power here is the same as the the denominator here is the same as denominator here. So I rewrote this in this simpler form. But it's still an integral over 3 parameters, alpha, beta, and w. All right, so now let's look at this result. So remember, this is the result of this two-loop Feynman diagram. Well, I have overall multiplying the integrals. There's a gamma of 4 minus d. So that's a gamma of epsilon. That's a 1 over epsilon pole. All right, so that's already divergent. We expected that. But there's another pole. There's another pole that comes from near w equal to 0. That's why I observed what happens to this p squared when w goes to 0. So let's see. Let's see what happens in this case. So I have this integral. So the integral is an integral over w. There's a power, 1 minus d over 2. And then there's some other functional dependence on w that is non-zero at w equal to 0. All right, so I make a trivial split. I write this function at 0 plus the difference between f from w minus f of 0. Now, this term will be a local term. Why is that? Well, as I said, this is divergent. Therefore, this will be finite. So I've subtracted the divergence, which comes from 0. So this will be finite. This integral will be finite. So what will have? We'll have this finite finite term multiplied by gamma of 4 minus d, gamma of 4 minus d, which is gamma of epsilon. That's, of course, divergent, but that's divergent, but the divergence comes from the one loop sub-diagram, right? Divergence came from here. That was the result of well, anyway, yeah, anyway, but the point is then that so we have this 1 over epsilon divergence, but there's no, but the result is local. That means no, sorry. What am I saying? No, no, it is non-local. Sorry, the second term will be non-local. It's the first term that is local. The first term will be gamma of 4 minus d, which is gamma of epsilon 1 over epsilon, and then this will be divergence, but this term does not depend on p, because we've seen that p squared when w goes to 0. No. Why am I? Yeah, I'm confused. When p goes to, when w goes to 0, I said that this p squared is proportional to p squared, little p squared. So why is this p independent? Oh, sorry. Yeah, the power. I'm sorry. Yeah, the power here is d minus 4. That was the point. Yes, that the power of p squared plus. So this depends on p, but the power here is d minus 4. So when I put d equal to 4, well, more precisely, d equal to 4 minus epsilon, then this goes to the power epsilon. So Um, so this is a lower divergence. The biggest the divergence of highest power in epsilon is the one which is this one over epsilon, times the one coming from w equal to 0. So when by the way, when w goes to 0, we obtain that this integral would be f of 0, which is something, but then times w squared to the 2 w to the 2 minus d over 2, the power, divided by w over divided by the same power, 2 minus d over 2, in between 0 and 1. So at 1 is nothing, it's just a constant, but at 0 this becomes 2 4 minus d. So this becomes 1 over epsilon. Again, I'm confused. It should have been w going to 1. That is divergent. No, yes, no, it's w equal to 0, because again, this is the power 4 minus 2 minus d over 2, which is epsilon. No. I think I did something wrong here. One to the power minus epsilon over 2 is still 1. So it's 1 over epsilon, okay. But 0 to the 0, on the other hand, is divergent. All right, so this is in any case 1 over 4 minus d, but I guess the point is that when w goes to 0, this is also divergent in W. I'm sorry, I don't understand anymore the reason why I have to put W equal to 0. Oh. No. No, sorry. Yeah, I think so f of W was 1 minus W over this. So f of 0 f of 0 was 1, but f of 1 was not 0. So I guess I'm just yeah, calculating this near W equal to 0. And then the result is 0 to the power, so W going to 0 to the power minus epsilon, or e to the power epsilon log W. Yeah, and I guess there's an issue of order of limits, and I think the term, so this term with f of 0 times this dependence at W equal to 0 gives, so f of 0 times e to the epsilon log W when this goes to 0. But if I consider epsilon going to 0 first, then this is no. No, I think on the other hand, no. I think I have to consider W going to 0 first. So I just write this as W to the epsilon, and epsilon is small but fixed, and then W goes really to 0. So then this f of 0 is multiplied only with the term W at 1 for this integral, and gives really this result, f of 0 over times 2 over 4 minus d. So that's that's a pole in epsilon, and we already had a pole in epsilon. As I said, the overall gamma 4 minus d, this was 1 over epsilon. And now this is also 1 over epsilon. So this is 1 over epsilon squared, and that means that this divergence is absorbed in a two-loop counter term. And then in this one, I have something that is constant, and in terms of epsilon, but there's this overall 1 over epsilon. So there's still a 1 over epsilon divergence, but the 1 over epsilon divergence will be local, since if I put d equal to 4, then this term becomes equal to 1. This term becomes equal to 1 if I put d equal to 4. Remember, this integral is finite. If I put d equal to 4, then this equal to 1, and I'm left with just an integral, a constant, an integral over w. So this is, oops, how did I do this? So this is now just a 1 over epsilon local divergence. So I have a 1 over epsilon squared constant divergence and 1 over epsilon local divergence. on the other hand, this is now the first term. This first term, as I said, had an overall 1 over epsilon squared. If I put in here, if I put d equal to 4, but if I put d equal to 4 minus epsilon, I can expand in epsilon. Or no. No, sorry. No, I was sorry. Yeah, I was talking about the divergence. So the divergences are local, but the finite part appears when I put in f of w. F of w has this p-dependent term. If I expand in epsilon, so this is 1 plus epsilon dot dot dot. So if I expand, then I get this local divergence plus a p-dependent part, and the same thing for the overall divergence. And the non-local part, this is complicated. The non-local divergent comes from multiplying from expanding this 1 plus epsilon. Then in here, I have the in here I have this constant, and then overall I have 1 over epsilon. No. I'm sorry, I'm messing this up very badly. I think I consider only this as f of w, and then I expand this in epsilon. And in this case, although I'm not sure why I would do this, but I guess just because I'm in and near w equal to 0. So there's the overall 1 over epsilon. And then by expanding this I get 1 times the divergence that comes from here, plus epsilon times the same divergence. This gives a constant part that is this this p squared of 0 plus m squared. And so finally, the divergence becomes the 1 loop, the 1 over epsilon divergence becomes this one. And this one will be cancelled by the 1 loop t plus u counter term, which was written here. So this was already the 1 loop integral, the 1 loop integral I2 times the vertex, the part of the counter term vertex that was constant, which was the I2 of 0. So this was, so v1 of 2 plus u was 2 times I2 of 0, and the 1 loop integral was I2 of p squared. And then the dependence on lambda tilde was, well, the counter vertex had lambda tilde squared, and then there's the other vertex, lambda tilde, that does not have a counter term. So the result is this one. So there's a gamma 2 minus d2 over 2 squared. That gives the 1 over epsilon squared divergence, right? But then these 2 integrals, each of which has the power epsilon. So I can expand in the power epsilon. And so really, I have 1 over epsilon minus a log, in this case, log m squared. And from this part, I have 1 over epsilon minus log of the p-dependent part. So we see that the non-local divergence, which is this times this, cancels, right? So this is 2 over epsilon minus log of this thing. And this is 1 over epsilon log of the same. And there was a factor of 2 somewhere. Oh, yeah, there's this factor of 2 missing, I guess. And again, we have also a 1 over epsilon squared constant part. that is part of the one loop, part of the intrinsically two loop counter term. So that's part of this. And this came from only the S channels, but then I have to use also the crossing to get the T channels and the U channels, but that's fine. Since we've removed the divergences in the S channel, the same will be true in the T channels and the U channels as well. So we have found finally the full renormalizability of the 4-point function at two loops. So as we see, there was at two loops we had a leading 1 over epsilon squared divergence that was constant and that needed to be cancelled by a new two-loop vertex counter term, and they were both independent one-loop divergences cancelling, and also this kind of non-local divergences, 1 over epsilon times log of p squared over m squared. And finally, the only thing to say is that the same thing generalizes to higher loops, and in general, we find where was it? In general, we find this kind of powers of logs. At higher loops, we'll find powers of logs. So log to the n of p squared over m squared in the finite part, coming from these nested or non-independent divergences times epsilon, right? So these will be called leading logs in the finite parts. All right, so this was what I wanted to tell you. Do you have any questions? Well, I don't know. Can you still hear me, or you don't hear me? And okay, no questions. All right. Good. That's it then. So I'll talk to you then on Wednesday. All right. Bye.